All right, 4.3, which is entitled Interaction Pairs and Newton's Third Law. I went on Google and I did a Google image search for Newton's third law and came up with a ton of really hilarious pictures that kind of demonstrate Newton's third laws. His third law. And Newton's third law is every action has an equal and opposite reaction. And that's in terms of forces, not necessarily motion or anything else, just the force. Like the force with which this is pulled out, the force of thrust, equals the force that's pushed forward. When you push forward, this happens on skateboards or on boats, and you'll see it. You'll walk forward, but then the boat will walk back. You sit down on something, gravity, and then this provides an upward supporting force. If you ever fire a gun, there's a force this way and a force that way, action and reaction. When you push on anything, whatever you push on it with is the force that it pushes back on you in the negative direction. So sometimes you'll see this negative right here when you're referring to Newton's laws. Force of A on B equals the negative force of B on A. So if this would be A, this ball would be B. Sometimes it's written like that. Here's a skateboard. You step off the skateboard walking forward, you push it backwards, action, reaction. Now again, it doesn't mean the motion, the velocity, the acceleration that this thing gets over here may not be the same velocity and acceleration that the skateboard gets. Here we've got two push people on skateboards. Newton's third law of apple consumption. Two people pushing each other. The force that they push on each other is equal and opposite. And lastly, hooking up, pulling on it with 500 newtons against the wall. We saw that the other day when we were talking about that problem where we draped them over the sides of the table. You could hold on to it and you still pull the force of 500 newtons. And 500 newtons, the scale reads 500 newtons. Our first example problem deals a little bit with interaction pairs, and it talks about the Earth. You have the Earth, and a softball. It has a mass of 0.18 kilograms. It's dropped, and its acceleration towards Earth is equal to g, the acceleration due to gravity. What is the force on Earth due to the ball? And what is Earth's resulting acceleration? So here's what's going on. Here's what it's asking. This ball is attracted to the Earth, and we call it a gravitational attraction. The Earth, no joke, is pulled back to it with the exact same gravitational attraction. To figure out, first of all, how much this gravitational attraction is, use F equals ma. What we're going to do is we're going to plug this in for the mass, 0.18, and our acceleration is 9.80. You multiply those two things together, and you get 1.76 or 1.8 newtons. So this gravitational force is equal to 0.18 newtons. Now, the amount of force that the Earth is pulled back up at it, 0.18 newtons. They are both attracted equal and opposite. It's tough to believe that the Earth is attracted to something as small as a ball, but it is. It's truly what's going on. It's attracted, and we don't understand how gravity works. But this wants us to know, what is the force on Earth? So the force on Earth due to the ball is 1.8 newtons. And what is Earth's acceleration? We're going to use F equals ma. The force that's exerted on Earth is 1.8 newtons. Oh boy, the mass of the Earth is 6.0 times 10 to the 24th kilograms. So this acceleration, my friends, is going to be very, very small. When you take 1.8 divided by 6 to the 24th, you get 3 times 10 to the negative 25th. That's really small. How small? It's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25 meters per second squared. That's a very, very, the Earth accelerates. It's super, super small, imperceptible, but that's what's going on. It kind of leads me to the question, why, Galileo, a long time ago, I have a picture of this in my room. It's the Leaning Tower of Pisa. You'll see people all the time. The Leaning Tower of Pisa. He dropped a very large ball and a very small ball from the Leaning Tower of Pisa. And it's funny because the large ball has a larger force of attraction than the small ball. But why, when you drop them, they both accelerate down at the exact same rate? How does that work? Why does the big one and the small ball, even though the big one has a larger attraction than the small, why do they take the same amount? Because their mass equally cancels them out. Because of this, F equals ma. It's perfect how this works. The big ball has a very large force, but it also has a very large mass. So then that forces the acceleration to be smaller. The small one, it's got a smaller force and a smaller mass, so the acceleration can stay the same. They equally and oppositely cancel each other out. The inertia from the big ball keeps it from accelerating due to the larger force. This is another example problem. It talks about tension. It says a 50 kilogram bucket is being lifted by a rope. So you've got a bucket here, and you're lifting it with a rope. This has a mass of 50 kilograms. We're lifting it with some unknown force. We'll call it the tensile force, because that's what ropes do. They exert things in tension. The bucket starts at rest. Oh boy, this is going to get complicated real quick. So the initial velocity is 0. And it's lifted 3 meters, so the distance it's being lifted is 3.0 meters. It's moving at oh my gosh. So the final velocity is 3.0 meters per second. If the acceleration is constant, I don't know what that is the rope in danger of breaking? So this kind of goes back to that day that I broke the weight with the yarn, broke the yarn with the weight. If I pull too hard on this, the mass of the bucket's going to prevent it from doing that, and the rope's going to snap. And the maximum force that we can exert right here, this is the maximum force, is 525. So let's see if we can figure this out. Okay, so I know, first of all, gravity. I know that gravity is going to be smaller. So when I first draw this, I know that gravity has to be smaller because it's accelerating up. So gravity is going to be smaller than the tensile force on the up. So I take 50 times 9.8, and I get 490 newtons. Okay. I think I can take all of this stuff and find the acceleration. So I think I'll use the one that doesn't have time in it, and it's VF squared equals VI squared plus 2AD. So 3 squared, 0, 2 times a times 3. Oh, this is kind of nice. So this becomes 9 divided by 6. 9 over 6 is 1.3 repeating. So acceleration is 1.3 meters per second squared going up. So I now know the acceleration. 1.3 meters per second squared. So now I can use Newton's second law. F equals ma. And remember, it's the net force. I have two competing forces here. I'm going to say that up is positive. I've got my tension force, and I've got a negative gravity. So my tension force, I don't know. I know gravity is 490. I know my mass is 50. And I know that my acceleration is 1.3. So I can now solve this for my tensile force to figure out, so 50 times 1.3, add 490, comes out to 555, or roughly 560. 560 newtons. Now that makes sense. It's got to be bigger. I know that my tension has to be bigger to get it to accelerate up, and oh boy, that's quite a bit larger. Is the rope in danger of breaking? Yes. And this is how engineers, when they design cranes or something that's hoisting anything, they know the maximum tensile force in a rope, and they'll program the crane not to accelerate it exceeding a certain acceleration so that they don't reach the limit. And then they also build in a factor of safety. Like a typical factor of safety would be 2 or even 1.5. So even though this has a 1.525 newtons, they'll build it and they'll say we're only going to do half of that, or like 262, you know. So they'll build this with the tolerances in mind, and they'll program the machine not to overwork itself as to break something or kill somebody. Our last bit to talk about today is the normal force. And we've talked about the normal force quite a bit. You know, the normal force is a supporting force provided provided by the surface, and it's parallel. It's always perpendicular. To the surface. So, I mean, for everything that we're doing right now, you have like a table and you've got a box on this table. The normal force goes up. But if we start having an inclined plane and you've got a box on it, the normal force is going to go at a right angle to the surface. It's always perpendicular to the surface. So there's 3 different scenarios here. You've got a box that's just resting on a table. You've got a box that you're lifting up, and you've got a box that you're pushing down. The normal force is different in all of these. The normal force is different in all of these. For instance, let's say that, just for argument's sake, that the weight of this thing was 100 newtons. So right now, the normal force is going to equal 100 newtons. It's just equal and opposite. Here I've got, I'm lifting up at 50. The weight of this thing doesn't change. It's still attracted to the earth with 100 newtons. But all the up forces have to equal all the down forces if this is not moving. So if I'm already pulling up at 50, then the normal force is equal to 50 newtons. In this case, it's less. There's less. The supporting force doesn't have to support as much because I'm taking some of the load with my hand. And then again, this thing weighs 100 newtons. But now I'm pushing down. Let's say I push down with a force of 50 newtons. So what is this thing? How much does the surface have to support? It has to support 150 newtons. So the normal force is variable. depending upon if it's being pushed down, if it's being pulled up. And this is what keeps like race cars. Race cars take advantage of the normal force. They have like those wings on the back that push them down, just like this hand is pushing down now, which gives you more friction. You can turn corners a lot faster. So kind of in summary, every action has an equal and opposite reaction. The forces are the same. The force that you push on something with is equal to the force that it pushes on you with. But that doesn't mean that they move the same. You drop a softball, and the softball traveling towards Earth is not going to be the exact same acceleration as the Earth traveling towards the softball. And you see that right here. The softball, we all know, accelerates at 9.80 meters per second squared. The Earth does not accelerate at 9.80. The Earth has far too large of a mass to do that, and it accelerates at a very, very small number, 3 times 10 to the negative 25th. Things, when you drop them, they go at the exact same rate, 9.80. Why doesn't the big one go faster? Well, because of its mass. It has inertia. It has to overcome that inertia, and that big force that it's got exactly overcomes its inertia. And then we talked about tension. We got 2 competing forces, and that's the net force. This net force is both tension and gravity. You have to put them both into your equation. You can't just pick one and put it in there. It's actually both.